A stone is thrown with a speed of 20 meters per second at an angle of 48 degrees to horizontal from the edge of a cliff 60 meters above the surface of the sea. A. Calculate the velocity with which stone hits the sea. Before calculating the final velocity, let us find the initial velocity in x component and initial velocity in y component. Initial velocity in x component is adjacent, so that is cosine theta equals to ux equals to u, and that is ux equals to u times cosine theta. Initial velocity is 20 times cosine 48 degree, and that gives us 13.38 meter per second. Y component of initial velocity is opposite, so that is sine theta equals to uy over u. So uy equals to u times sine theta. Initial velocity is 20 times sine 48 degree, and that gives us 14.86 meter per second. We choose of what is a positive reference. Acceleration due to gravity in y component equals to minus g, as acceleration due to gravity is downward direction. So displacement is downward, so that is minus 60. The ball hits the sea when the vertical displacement is y equals to minus 60. So let's write it down, the displacement equation. S equals to ut plus 1 over 2 at squared. Let's write it down y component. Displacement is minus 60 equals to initial velocity in y component equals to 14.86 times t plus 1 over 2 times minus 9.81 times t squared. Solving for positive roots, we find t equals to 5.33 seconds. Let's write it down, the velocity formula. V equals to u plus at. Acceleration in x component equals to 0. That gives us vx equals to ux. And initial velocity in x component is 13.38 meter per second, which means the velocity in horizontal component is constant, 13.38 meter per second. In a similar manner, let us find the vertical component of final velocity. Let us write it down. Y component, vy equals to uy plus ayt. And vy equals to initial velocity in vertical component is 14.86 plus minus 9.81 times time taken is 5.33, and that gives us 37.43 meter per second. That is 37.43 meter per second. Final speed equals to v squared equals to vx squared plus vy squared. Vx squared plus vy squared. Let's plug in the values. 13.38 squared plus, since the final velocity is downward direction, that is minus 37.43 squared, and that gives us 39.4, approximately 40 meter per second. Since the velocity is a vector quantity, we need to find the angle. So tan theta equals to opposite vy over adjacent vx, and theta equals to tan vy over vx. Theta equals to tan minus 1. Final velocity in y component is equals to minus 37.43 over final velocity in x component 13.38. That gives us minus 70 degree. That means this angle is 70 degree. And the velocity equals to 40 meter per second. Discuss qualitatively the effect of air resistance on your answer to a sum of the kinetic energy of the ball will be converted into thermal energy, and so speed at impact will be less. The horizontal component of velocity will decrease in the course of motion and will tend to go to zero, but a vertical component will never become zero after reaching the maximum height. This means that the angle of impact will be steeper. A stone of mass 0.20 kilogram is thrown with a speed 22 meters per second from the edge of cliff that is 32 meters above the sea. The initial velocity of the stone makes an angle of 35 degrees with the horizontal air resistance is neglected. Determine the horizontal and vertical component of initial velocity. Horizontal component of initial velocity is adjacent. That is cosine theta equals to ux over u. Ux equal to u times cosine theta. Initial velocity is 22 times cosine 35 degree, and that gives us 18 meter per second. Vertical component of initial velocity is opposites. That is sine theta equals to uy over u, and uy equals to u times sine theta. Initial velocity is 22 times sine 35 degrees. That gives us approximately 13 meter per second. A sketch graph showing the variation with the time of horizontal and vertical component of velocity. Okay, let us focus on the horizontal component. Velocity formula v equals to u plus at. Let's write it down. X component vx equals to ux plus axt. Acceleration in x component equals to 0. So vx equal to ux. Initial velocity in x component is 18 meter per second, which indicates that velocity in x component is constant, and that is 18 meter per second. Now let's focus on y component. Velocity formula v equals to u plus at. Write it down. Y component vy equals to uy plus ayt. We choose upward as a positive reference, and acceleration due to gravity is downward. So ay equals to minus g. Let's substitute values. Vy equals to initial velocity in vertical component is 13 plus minus 9.81 t. That gives us Vy equals to 13 minus 9.81 t. This graph is a linear graph. Initial velocity is 13 and gradient is minus 9.8. This is 13 and gradient is minus 9.81. And we can actually find the time taken here. At the maximum height, the vertical component of velocity becomes 0. 13 minus 9.81 t. T equals to 1.3 second. Here is 1.3. A stone of mass 0.20 kilogram is thrown with a speed 22 meters per second from the edge of cliff that is 32 meters above the sea. The initial velocity of the stone makes an angle of 35 degrees with a horizontal air resistance is neglected. Bi. Calculate the maximum height above the cliff reached by stone. So we don't know the time. We probably use a timeless formula for this. V squared equals to u squared plus 2as. Let's write it down. Y component vy squared equals to uy squared plus 2ay sy. Let us choose upward as a positive reference. Ay equals to minus g as acceleration due to gravity is downward direction. At the highest point, vertical component of velocity becomes 0. So 0 squared equals to initial velocity in vertical component, that is 13. 13 squared plus 2 times minus 9.81 times sy. So that sy equals to 13 squared divided by 2 times 9.81. Which is equals to 8.6 meter. That means this height sy equals to 8.6 meter. B states the net force on the stone at the highest point in its path. The only force acting on it is the weight. So W equals to mg. Mass is 0.20 times acceleration due to gravity is 9.81, and that is 1.96 Newton, or 2 Newton as two significant figure. Using conservation of energy determines the speed of the sun as it hits sea. At the initial position, we have initial kinetic energy and gravitational potential energy. And at the surface of the sea, we have the final kinetic energy. As the air resistance is neglected, mechanical energy is conserved. So 1/2 mu squared plus mgh equals to 1/2 mv squared. Masses are cancel out. So you get 1/2 u squared plus gh 1/2 v squared. Both side times 2. You get u squared plus 2gh equals to v squared. We apply root square to both sides. We get and plug in the values. Initial velocity is 22 squared plus 2 times 9.81 times the height is 32 meter. That gives us 33.3 meter per second. Hence, or otherwise, determines the time it took the sun to reach surface of the sea. The time is determined by y component. So method 1, use displacement formula. S equals to ut plus 1/2 at squared. Let's write it down. Y component sy equals to uyt plus 1/2 ayt squared. We choose upward as a positive reference. Acceleration due to gravity in y component minus g, which is downward direction. Since the object is moving downward direction, the displacement in y component is y equals to minus 32 equals initial velocity in y component 12.6 times t plus 1/2 times minus 9.81 times t squared. Solving for positive value, we get 4.1 second. We're going to use the second method. Final velocity squared equals to vx squared plus vy squared. And final velocity in y component equals to vy equals to v squared minus vx squared. Plug in the values. Final velocity is 33.3 squared minus x component was 18 squared. That gives us 28 meter per second. As the upward is a positive reference and object is moving downward, so final velocity in y component as a vector minus 28 meter per second. Now let us use velocity formula. V equals to u plus at, and y component vy equals to uy plus ayt. So let's plug in the value. Final velocity downward, which is minus 28. Initial velocity is initially upward, that's 12.6 plus minus 9.81 t, and t equals to 4.1 second.